Good afternoon and welcome to Bitcoin and Blockchain 101 with James Turner. Before we start the webinar, just a quick introduction to eSynergy Solutions. eSynergy specialises in open source and cloud resourcing. Should you be looking for a new role or be looking to build out your team, please get in touch. Now, moving on to some housekeeping. If you have any questions for James, please fire them over via the question box throughout, and James will answer them at the end of his talk. We are recording the session and the slides and recording will be made available and sent to you tomorrow by email, along with my contact details. Now I'm going to pass you over to James to begin talk.
Let's see if we can get this on the screen, shall we? Okie dokie, there we go. Alright, I think everybody should be able to see this now. Okay, so this is the Bitcoin and Blockchain 101. So let's kick it off. I should probably start with who am I? So this is me. This is me eating ice cream. I am a polyglot programmer. So what does that mean? It means I've programmed in a multitude of languages and I've accumulated over 10 years worth of experience working in different languages with different technologies for different companies, some of which are people like eBay, BBC and Skype. So big names that you've probably all heard of. Right now, I'm heading up a team at a small startup called Magna.com, dealing with, as you may have guessed, Bitcoin and blockchain related technologies. So, what's on the agenda? These are the topics I'm going to cover. So how you might know about Bitcoin, where does it come from, what is it, how Bitcoin sort of solves certain problems, why it came around in the first place, what does it do, and then talk about blockchain, this thing that everybody's talking about. It's magical, it seems to be sort of solving everybody's problems. And then I'm going to go why it's not magical as might think it is. And we'll just go over a recap, talk a little bit about companies that sort of are on the fringes, the edges of this technology, and then we'll deal with some questions at the end. So let's begin with what is not Bitcoin. So quite a lot of you have probably heard about Silk Road. Silk Road is not Bitcoin. Silk Road was a marketplace for drugs and narcotics. It just so happened to be using a currency called Bitcoin. Now, I don't associate Bitcoin as a bad thing because it's being used in a bad way, much the same way I don't attribute the dollar as being because it's used in other forms of criminal activity. In that vein, this is not Bitcoin. Silk Road is not representative of Bitcoin. For example, we're based down near Old Street. There is a shop down here called Accept Bitcoin for Soup. Again, it's the good side. It's not Silk Road entity, but in the same vein, soup is not Bitcoin. So what is Bitcoin? This is Bitcoin. Bitcoin is really just a zeros and ones given interpretation have a meaning. So it was created by a guy called Satoshi Nakamoto, supposedly a Nakamoto. And it was based on previously, back in the 90s, such as B-Money and Hashcash, technologies which were brought around to solve problems. So Bitcoin's a protocol, fundamentally, and so consequently that means that it's exchange of data over a network, and it's a set of rules that people adhere to. And for peer-to-peer protocols, the HTTP protocol, these are protocols which can be very simple to check that they are right or wrong. In the case of Bitcoin, the protocol describes a transaction that typically occurs between one or many parties. So let's trace back a simple example of a monetary transaction. So banking Alice and Bob, a typical situation that you might experience of dollars right now. So, Alice, and you want to send your friend Bob some money, in this case, £100. But in order for you to do that, you need to have coordination with your bank, your institute, the person who's handling your money. So in this case, Alice asks the bank if she could send £100 money to Bob, who is also a resident of Bank B. Now, this requires coordinated effort. Bank A and Bank B have to work together. The £100 Alice's account gets correctly deducted from her ledger. So if you have a Bank A ledger, the top entry there is Alice. She is not worse off. B now has to contribute the £100 to Bob. Now in this situation, Alice has to trust that her bank is facilitating the request that she's asked them to do. And she actually has no way of verifying that this has been done without communicating directly with Bob. She has no way to make sure that Bank A and Bank B are coordinating correctly, and that Bank A is going to take £100 away from her, and Bank B is going to attribute £100 here. And really, they can be broken down into three fundamental areas. So they come down to these things. Centralized system failure. And we've seen this in real life, in the real world. NatWest and RBS several times in the last year have had ATM glitches. Now, at those points in time, that meant that customers who are in their supermarket buying goods were able to pay for those goods because their bank had failed. There was some form of failure, which meant that their cards were being rejected at the till. It also meant that people trying to withdraw cash from ATMs were unable to do so. Consequently, the consumer had no control over this. They couldn't decide to use the money that they knew they had and spend it the way they wanted to. They were beholden to a system which was not theirs. This also brings around the issue of centralized trust failure. And we've seen this in the financial crisis of 2008 and 2009. There was a very large bank run at Northern Rock. Now, everybody who was a Northern Rock customer at the time had to trust that Northern Rock, A, were looking after their money correctly, which, as it turns out, was not the case, and B, when they went out of Northern Rock, the Northern Rock were able to facilitate that for them. They were going to be able to give them back the money that was in their bank account. The issue here was that those people actually couldn't get the money out of their bank account. They queued for hours in front of the Northern Rock Building Society, and they were unable to get the money out. A lot of people lost a lot of money, and amongst other things. And thirdly, separated ledgers. There is no, if you look back at the previous slide, there is no single state of view for the ledgers between these two banks. They're separated. So if you are HMRC, if you're the Met Fraud Squad, if you are KPMG and you're doing an audit and you need to verify that some transactions, some money movement between Bank A and Bank B occurred, you can't do that. There's no easy way for you to do that. You have to convince Bank A and Bank B to give you a set of ledgers, which you hope they haven't doctored, and trust that that information is going to be correct, and do the merge verification yourself. You don't have copies of that stuff, so you need to request them. So let's look at Bitcoin, Alice. How does this differ? So really, there's a big fundamental difference here. So where we had Bank A and Bank B, and they were separated into Bank A's ledger and Bank B's ledger, now we have one ledger. And instead, everybody has the same copy of the ledger. So in this case, we can see that Alice has an identical copy of the ledger as Bob. Now these are consumers, so every consumer has a copy of the ledger, which means they don't go to a centralized system, they don't need to go to a centralized trust unit and ask for that information and hope that that information is manipulated by a third party. So when it comes around to doing that same transaction that Alice originally wanted to do, he literally just has to create the transaction, update her own ledger, and tell everybody else about it. So here we can see Alice has deducted £20 from herself, attributed £20 to Bob, and tells Graham, Dave, Steve, and Bob about this transaction, and they all update their ledger to be in the same state. So what we've done here is we've solved those very problems that the banks presented us with. Your centralized failure, your split ledger, and your centralized trust. So we now have fault tolerance. So if Alice drops out of the system, if she gets run over by a bus and her ledger is on her phone and it gets crushed, it's not a problem because that same ledger exists everywhere else with all the other consumers. So it's fault tolerant. We also have no centralized trust. So no one person in this ecosystem is responsible for making sure that everything is correct. And thirdly, it's auditable. Every single person in the ecosystem has a copy, so they can verify for themselves that the transactions have occurred the way they should have done and that money is attributed to the correct people. So, great success, right? Now taken with the three fundamental problems and fix them. They're done. See you later, banks. There's no need for you anymore. Except that's not quite true. So where we've taken our original problems and we've now solved those, we actually have a new set of problems instead. So let's look at the case of Evil Alice. Evil Alice is a corrupt actor in our system. In this particular example, she wants to double spend. Now what do I mean by double spending? So if we look at the diagram, what Alice is now going to do is she's going to create two transactions. The first transaction is to subtract £100 from herself and give £100 to Bob. So she creates that transaction and she tells Bob about it. But at the same time, Alice will create a second transaction which deducts £100 from herself and gives £100 to Graham. He has now spent that £100 twice. So this is known as double spending. And we have a knock-on effect here. We have two ledgers in our ecosystem, one owned by Bob, one owned by Graham, that differ. So in Bob's world, Bob thinks he's £100 better off. So Bob's happy. And in Graham's world, he thinks he is £100 better off. So he's happy. But these two ledgers that are separated with these two people actually differ. And this is an incorrect state, a bad state. So, how do we fix this? Well, let's first go and look at the ledger. Like, original ledger was a very simplified ledger. You just kind of attribute to credit and you debit money from the relevant people. So now if we expand that a little bit, we can take a transaction and we can split it up. So let's assume that Alice has £100. If we think about this as a cash transaction, something we might do in a shop, we'd go in, we'd have a £100 note, and we would pick up our product and we'd take it to the till, and we would hand over that £100 note and we would get some change. So we would effectively split our £100 note into the amount we're giving the retailer and the amount of change we're giving back to ourselves. So we can see this in this adapted form of the ledger because the top two ends are transaction Alice and Bob effectively. So in the first entry, you see that Alice has attributed £80 to Bob. From Alice, it's to Bob, and the amount is 80. But at the same time, because Alice only had a £100 note, she has to change. So Alice also sends 20 of that 100 from herself to herself. So we now have a split transaction. It's split into the sending and change part of the transaction. So let's adapt this a little bit further. We can apply IDs to this information. So we can say that the first transaction, transaction 1, is split into two component parts, index 0, 1. So in this case, transaction 1 is from Alice to Bob, and Alice gets change. Transaction 2 is from Bob to Graham. Now Bob spent the whole £80 amount, consequently gets no change. So transaction 2 only has one index. Transaction 3 involves Graham returning some money to Bob and giving himself some change. Again, splitting down that amount that he originally had and attributing change component to himself. So if we take this a little bit further, we can now reference every new transaction with a spend from a previous transaction. So let's look at transaction 2.0. In 2.0, we are sending transaction 1.0. Transaction 1.0, which attributed £80 to Bob. Bob spending that £80 onto with no change. The same can be applied to transaction 3. Transaction 3 spends transaction 2.0 and splits it into two parts. So the £10 goes back to Bob and the £70 is given as change to Graham. Now if we add an additional column to our ledger, we can mark things as spent or not spent. So in the case of transaction 1, we can see that it's been spent because it got spent by transaction 2. We can also see that transaction 2 also spent because it got spent by transactions 3.0 and 3.1. So we can actually build a balance from this information, from this ledger. If we take all the unspent amounts and the people they're sent to, we can build a balance. So transaction ID 1.1 attributes £20 to Alice. That's the only transaction part which is onto Alice. Consequently, we know Alice's balance is 20. And the same can be applied for Bob and for Graham. We can see their unspent components being attributed to them as a balance. So, where does blockchain come into all this? Because we've seen how the ledger is adapted. We see how the ledger references one transaction to the previous one. So now, if we take those transactions and we group them up, we can call a block. It's an aggregate of transactions. So in block 1, in this example, we've taken transaction 1 and transaction 2, and they've formed block. Now if we take transaction 3 and put it into block 2 and reference block 1, we can see that we have a chain of blocks. A block is simply taking some information, aggregating it into a form, and referencing the previous block of information. So how do I go about creating one of these blocks? How do I get into a blockchain situation? How can I a blockchain? So in Bitcoin, this is done by taking some recent transaction data and a reference to the previous block, which as we know is also an aggregate of transaction data. We produce a hash of this data. So we take all the transactions that are involved, pass it through an algorithmic computational function, which gives us a hash. And then we add this new block to the chain of blocks we already know about. And we repeat that process ad infinitum. So we need to cover what hashing is. You know, how does hashing get involved here? So as an example, let's take a sentence: the quick brown fox jumps over the lazy dog. Now, if we use the SHA-256 hashing algorithm, for example, and we pass in this sentence a hashing algorithm, we get the output starting D7. And this output is essentially random. For the purposes of computation, it's random. Now, if we take that same sentence again, and we change the last letter, so the quick brown fox jumps over the lazy dog, and hash that sentence, we now get a completely different hashed output. So we can see that just by changing one letter in a sentence, the hash result is extremely different, essentially providing us a form of randomization. So let's go back to creating our block. If we make our block 1, which we know contains transaction 2, we hash that, we get the hash that begins with 5A93. That's the hash of the data that's in that block. Now when we come to creating our next block of data, which we know is block 2, and we know it contains transaction 3. When we hash that along with the hash from the previous block, we get another hash. And we apply that again. So at height 2, we take transaction 4, we hash it with the previous hash, and we get another hash. So what does this give us? Why are we doing this? Let's do something a little naughty. So say we wanted to alter transaction 3. We decided that we wanted to change the value that the recipient was getting. So instead of them getting £100, we've decided they get £0, because we're mean like that. We don't want to give them any money. So if I change transaction 3 and it becomes transaction 3.1 because I've changed some data, when I come to hashing that block again, I get a completely different hash. The same hash as my original transaction 3 would have given me in that block. Consequently, the next block up, which contains transaction 4, because it references the previous hash and is itself hashed, we can see that they no longer tally up. So the new hash we've generated, 60DA, the invalid block we'll call it, is no longer referenced by the block that's one higher than it. So we see that some data in that block's changed. This gives us a property of immutability. We cannot change information in a historic block without affecting the hash result. And so consequently, any block further along the chain will believe that that other block that's generated is invalid. It doesn't fit. Now, you would argue that, well, I can change block 2 and I can change block 3 as well. I just rewrite block 3 to include transaction 4 and reference my newly created block 2.1. And I now have a full chain again. So how to get around this? This is where block difficulty comes in. So the question is, what's to stop Alice from rewriting all those historical blocks? She wanted to change transaction 3.1, 3 into 3.1, and she wants to rewrite history. Well, the hashing that's involved in generating this blockchain is complex enough that it takes a long time to produce a block. A block is valid. And so Alice actually cannot guarantee that she's going to be the next person to mine the next block. And how's this done? So most cryptocurrencies, we're talking Bitcoin, coins, doggy coins, they all rely on this notion of difficulty. We're generating those hashes for blocks. The validity, a valid block is a hash that conforms to a certain pattern. Now in the case of cryptocurrencies, that pattern is that there needs to be a certain number of 0 bits at front of the hash that gets generated. If the hash conforms to that format, then it's a valid block. Now, given that hash is random, you cannot guarantee generating a block that has a sufficient number of 0 prefixes in it for it to be valid. And so this is known as proof of work, or you may have heard of the term mining. That's essentially what this is. It's to generate a block with a predisposed format for its hash. So let's go back to our double spending example of evil Alice. So in our original example, Alice generated 2 transactions, spending £100 twice, once to Bob and once to Graham. However, because we can now verify that blocks of data are correct, and it takes time to do that because we require a particular outcome, eventually a block will be that gives us the state of the ledger. So in this particular case, a block was generated by Bob, which included Bob's transaction and is a valid block because it contains the right hash prefix. And so we now have a valid block that usurps Graham's knowledge of the ledger. So Graham replaces that with his copy of the ledger. He now has a update consistent ledger. Now, it's a bit unfortunate for Graham because he is now not £100 better off. Bob got that £100. But what we have here is eventual consistency. So eventually, the state of that ledger becomes consistent amongst all the actors. So in this case, Bob got the £100. So why bother? Why bother generating these blocks? You know, what's my incentive as an actor in this system to actually generate a block for everybody else to give a consistent state of the ledger? So in the case of Bitcoin, the protocol basically says that if you generate a block, you can put a transaction into this block that attributes you, the miner, with a reward. So in the case of Bitcoin, initially the reward was 50 Bitcoins. You actually got some system contribution. This is actually decaying over time. So the block reward decays over time. It's essentially a function, which means that when it started it was 50 Bitcoin, now it's 25 Bitcoin. It will decrease kind of exponentially towards 0. So the reason to participate is the reward. Reward of mining a Bitcoin, or mine some Bitcoins or transactions, or giving a consistent view of the ledger, actually of a greater benefit to you as an actor than trying to usurp it, for example, or trying to manipulate transactions in some way. So more of an incentive to be a good actor, be a good citizen. So no more double spends. That problem, right? That problem's gone away. We now have a consistent view of the ledger, eventually. Not quite. So we're almost there. We have a different problem now. Now Alice decided Graham's money instead. So Alice, she did before. She generates a transaction, but this time she deducts £100 from Graham and gives it to herself. And so she tells Bob about it, and Bob goes, oh, yep, transaction, that's fine. I did it. But Graham gets it, and he's like, woo, don't think so. Nope, you can't have that £100, I did not authorize that. We have a different problem here. Someone else trying to spend money. How do I know that the cash you're giving me belongs to you? How do I know you're spending your money? This is where the cryptographic element of cryptocurrencies comes in. So as a primer of cryptography, cryptography really is just mathematics. A set of provable mathematical equations that you or I or anybody else set the same output with the same input. So we can all run the same functions. I know that if I do a 1 plus 1, I'm going to get a 2. If you do a 1 plus 1, 2 as well. Bitcoin uses asymmetric key cryptography. Now, this is cryptography based on public and private keys. And to give you an analogy, I might say that if you own a house, it has a front door. And in the front door is a lock, which takes a key. Now, everybody who walks past your house can see your front door and can lock. That is a public-facing part of that component. However, the only person who can unlock that door is you. Because you own the key to the door. So that's a very similar thing, public-private key cryptography. The two component parts, a public key, private key. Everybody can see the public key. That's not a problem. But without the private key, they cannot unlock the component parts they need. So in the case of Bitcoin, this public key component is known as the address, and it's used as the address for which to send people money. And because this is cryptography, there's no reliance on an intermediary partner or party to provide the account numbers. So I can generate myself a private key. I just need a computer, just like anybody else. I don't need to rely on third-party trust authorities such as a bank or some other intermediary, PayPal for example, to generate an account number and a sort code for me. I can do it myself effectively. So let's go back to Alice, Bob, and Graham. We can now assign Alice and Bob and Graham some public and private keys. They can generate themselves. In this particular example, I've used some very trivial hexadecimal numbers, just to keep it short. So here you can see the public and private keys for these three individuals. Now, if we take this to our ledger, this is our original adapted ledger, we can now apply those public key parts to the ledger. We all acknowledge that the public key part is public. It's allowed to be seen by people. The private key part does not exist in ledger. So here we can see Alice and Bob and Graham have all been sort of superimposed by their public key parts. Now what this does is gives us an anonymous ledger. So I can no longer determine that the key, the public key AABC4D is actually Alice. I don't know it's Alice, I just know it's AABC4D. I know the transaction occurred between that key and another key. So I now have an anonymous ledger. I'm hiding some information. I'm no longer giving away information that I don't expose to the public. And we can take this one step further. Because we're using public-private key cryptography, I can provide a signature on a transaction. Very much like you would put your PIN in for your debit card, or you would sign a receipt if you were forced to sign a receipt for a purchase of goods. So we can now provide a signature for the transactions to verify that the person whose public key is going from is able to spend it. So in this case, we can see that transaction 1 is going from Alice to Bob and some change for herself. We can sign those component parts using the public-private key cryptography aspects. And these are now valid signatures. I can verify that signature is valid for Alice or her public key. So let's go back to our transaction, where Alice is spending Graham's money. Now, Alice generates those transactions as she did before, but now she has to provide a signature. The problem is, Alice doesn't have Graham's private key, so she can't generate a signature on that transaction. Consequently, when she tries to tell Bob and Graham about it, they reject that transaction because the signature is either not there or invalid, because Alice does not have the private key parts that she requires to create the signature. So not bad, right? We've now gone from a system that had centralized trust and centralized failure and a split ledger into a system that now has a distributed ledger that is eventually consistent and verifies part of the transaction using cryptography and anonymous. We're not giving away any information, even though it's public. However, it's not all that shiny. So some of the issues, as I explained before, when you solve some problems, you tend to generate some more problems. Bitcoin is very consistent. We saw in the case of generation blocks that eventually gets into a state where everybody agrees. So in the case of Bitcoin, it takes about 10 minutes for that to happen, roughly. This means if you're talking about high transaction volume systems, so talking about your Visa card, your MasterCard, your Swift networks, that is not going to work for them. They need immediate consistency. They need something that is resolved in nanoseconds, not 10 minutes. So for that volume, Bitcoin is probably not going to be the answer. In fact, blockchains that have eventual consistency are not going to be the answer. It's also non-rescindable. Once you've issued your transaction and told some people about it, money is gone. So where we took away our original trust to third party, go to them when we accidentally send somebody some money and say, oh, I'm really sorry, I sent somebody who wasn't supposed to send money some money. Please can I have it back? In Coin Protocol, once you send that money's gone. That person gets it, and you don't have it anymore, and you can't ask for it back. It's made worse by the fact you can't identify people in your ledger, so you don't, even if you wanted it back, you wouldn't know who to go to. Lots of private keys. So where we were placing our centralized all our own keys, we now hold the ability to unlock our own money. Consequently, it actually puts a lot of onus on us to deal with our own security problems. So if I accidentally drop my hard drive and crack it, and the data on there is unrecoverable, and that hard drive had to hold my private key, well, I've got a little bit of a problem. I can't unlock that money anymore. So sure, the money still exists in the ledger, but I can't sign any transactions that will actually spend that money onwards. So I have a bit of a problem. Private key loss is an issue. And right now, we lose approximately 1% of Bitcoin a year. So it's dwindling, not by a lot, but it's getting somewhere. People lose their keys. There's a great example of a guy who had a lot of Bitcoin on a hard drive, and then he went to replace the hard drive in his computer and threw his old hard drive in dump, and later he finds out Bitcoin's worth all the money, and all of a sudden he has a deep desire to go reading through a dump to find the hard drive that he lost. He didn't find it, incidentally. And so lastly, change rollouts are hard. We're talking about distributing software to people globally, where each person essentially runs the same software and they all agree on the same format for the protocol. Now, when it comes to changing that protocol or making alterations, we actually have an issue. We have to convince everybody to change their software at the same time. Now, company and IT tussling out the top. You know that is a process that's long and arduous process and is prone to failure. So imagine that, but on a scale where you don't or not Bitcoin software so many of that blockchain
Hi, James.
Am I back?
Yeah, got you back. Thanks.
I'm back. Shall I carry on?
Yes, please.
I'll take that as yes.
Sorry.
That's all right. Security. So we now have a system that is secured by mathematics and cryptography, not secured by a centralized trust authority. I don't have to trust that the bank is correctly holding my money and that they're not going to accidentally lose it somewhere. It's not a problem I have anymore. It's anonymized. So yes, my transactions are publicly viewable, but people can't actually attribute them to me because they have no metadata about transaction. They don't know that Alice, Bob, or Graham are trading. All they can see is public keys. So we have anonymization. It protects the user in a system where they now no longer have to hand over personal information in order to transact. And it's a system that rewards participation. So it's much better for me to be a good actor, to participate, to contribute to the network and to mine, than it is for me to attempt to subvert it and shut it down and do things that I'm supposed to do. It costs me more computing power to rewrite the blockchain and rewrite all that transaction history than it would for me just spending that same computing power trying to mine a block where I get a reward. So applying some game theory there, it makes more sense for me to be a good actor than a bad actor. So it gives us all these aspects, and it solves some of our original problems. It was pretty good. So what are the people doing with Bitcoin? So we've got a few examples here of people that have kind of Bitcoin, and they're applying it in either the Bitcoin ecosystem or in similar ecosystems. So we'll look at a few of these. We've got R3, the Blockchain Consortium. I'm sure most of you have probably heard of these guys already. They are doing some interesting work in kind of providing blockchain solutions to banks and financial institutions. They're kind of collecting a consortium to kind of work together and solve some of the problems that banks have. They are not using Bitcoin, but the Bitcoin technology in a. So they're looking at certainly the things like the immutability of transactions and the security, and they're fixing the issue of consistency and applying that to where you have things like contract exchanges. You've also got people like Hedgie who are doing smart contracts. You've got people like Hyperledger Project who are trying to implement blockchain-like technologies in the Linux kernel. And then you've got your kind of more run-of-the-mill companies like Gift and Purst.io and Zappo, kind of providing us those financial backbones to Bitcoin, the ability to spend your Bitcoin, spend it at a particular source. So Purst facilitate spending at Amazon, I know from what I've read. You've got people like Factom who are actually using Bitcoin's blockchain to tie medical data into the blockchain to essentially create immutable sets of medical records. So if we think about our blockchains, if we go back a little bit, instead of transactions, if we take surgical procedures and we digitize those, so we could digitize it into, let me think, so a surgeon, name of the surgeon, we could have the name of the patient and the type of the operation, that would action if you like, and we could take a series of those and we could package them up into a book, and we could hash it, and then we could pin that into Bitcoin's blockchain. We could write a transaction in Bitcoin blockchain and append some meta information about the Factom record keeping service that indicates that it's essentially time-stamped that piece of data. And so we've got Magna, is who I work for. We're also in the sector of financial services. Basically, we provide Bitcoin savings accounts very much the same way that sort of gift cards and Purse and Zappo provide services. We provide those similar sorts of services. And then we've got Everledger, who are very much like Factom, and they do diamond tracking and verification of source of diamonds. Quite an interesting project. It's been around for quite a while now. Certainly has some legs. I think it's seeing some take up with the big diamond producers. So that's what some people are doing with Bitcoin. Hopefully it makes you think a little bit more about how you can apply sort of protocols, transaction protocols and blockchain-like technology into things you do, and acknowledge the problems that it sort of solves for you and the problems that it will present as a consequence. So with all that being said, do we have any questions? I can find them. No, can't seem to have my screen share. Let's try that again. Shall I hand it to you, Adele? I think I will.
Hi James, we've got a couple of questions, just struggling to find which James to send it to. So we've got one here from Oza Okol, and it's asking, what's any applications insurance? Is it possible to do it in insurance?
Well, so very much like Factom are doing, if you consider insurance as essentially a contract between two parties. So if you've got the insurer and, I mean, don't get me wrong, I don't know a huge amount about insurance contracts. I'm going to make it down to something simple. So if you've got the insurer, the person who's issuing the insurance for example, to cover you for your car or whatever, and you take the person who's taking out the insurance, you take those two component parties, you could write in some of the legal part of that contract, and you could hash that information to generate essentially a number. And then you could take this and form it into an aggregate block, and you could chain it along. You essentially get an immutable state of legal, and they would be timestamped because you know roughly when a block kind of occurs and becomes immutable. So yeah, sure. I mean, you could certainly take some of the things that apply to blockchain technology and apply them into assurance. There's no reason why you couldn't. It really comes down to kind of what problem you're trying to solve. So is the problem in insurance that you have no time-stamped records of when contracts were taken out? If that's the case, then you essentially need an immutable time-stamped record-keeping system. Something blockchain-esque might work for you. I hope that answers that question. And I think we've got another question here. So, who funds the? This is from Derek Colley. Who funds public record keeping of the ledgers? Okay, so in the case of the Bitcoin ecosystem, the person who's essentially funding it is the miner. They're the person who's expending electricity to verify all the transactions in a block. So that is essentially fundamentally the answer to the question. You know, if miners, and they do it because they get a reward. So if I, as a miner, I generate a block, I get 25, 50 Bitcoins. So I'm incentivized to verify the records in the ledger. That's my incentive. So the people who are funding it are basically running the computers doing the mining. It's as simple as that, really. And so we've got another question here. Other efforts to speed up the transaction time to 10 or more minutes using a bit.ly-like address for longer chains. And that's from Bobster Falvey. So my understanding at the minute is if you speed up the verification of those transactions and reduce the time for your ledger to become consistent, then you run the risk of having more things like block forks, making eventual consistency in a network much harder to do. I don't know that there are any particular efforts. I know that the latest part of the big proposals is to do something called segregated weights, which allows us to do verification of blocks without verification of transactions, something along those lines. I don't know a whole lot about it, but I think there is. I think essentially that's looking at kind of speeding up the volume of transactions that you can get through. You still need block generation to take time because otherwise people can build on these subvert systems. So I think your eventual consistency of 10 minutes will still stay, but the speed at which transactions can be applied and the volumes which they can be applied will probably go up. So I got another question here. What's required to become a miner? And that's from Marcello Galati. So you just need a computer and a bit of software. It's essentially what it comes down to. Right now you can download, there's some mining programs out there. There's the Bitcoin Core, which you can download and run if you really wanted to kind of contribute to the network and become a miner and hopefully, you know, get the reward from mining a block. My only advice in that particular situation would be that unless you're going to join a mining pool, it's probably not worth doing. And just to clarify, a mining pool is essentially a collection of miners who operate as a single entity. So that works by, say you and I, Marcelo, were to contribute one computer each and we would both run the program at the same time. If one of two of us generated a block, our agreement would be we would split the reward out of that block 50-50. So I reward and you get half the reward. And that's what a mining pool is. And there are at least 5 or 6 well-known mining pools operate in this fashion. We're talking thousands, maybe tens of thousands of miners in these pools, and consequently the rewards are kind of split into very small component parts. But the probability of mining a block on your own with a small machine is highly unlikely. So if you're going to do mining, I would suggest joining a pool. But in order to become a miner, you just need to download Bitcoin Core and run it on your computer. It's about all you need to do, really. I don't think there's any other questions. We've still got some left if people want to ask any further ones, or if you've got any questions for me, Adele, if you're still around.
Yeah, no, that's perfect. So there's one more. It's from Marcelo again, and he's just asking more about your business.
Oh, so Magna.com. So we originally started out as a Bitcoin trading derivatives platform, formerly known as BTC.SX, but we rebranded about a year and a bit ago. So we originally allowed you to trade on the price of Bitcoin to the dollar. So, you know, you could place a long trade derivative, for example, 10 to 1, and if the price of Bitcoin went up, then you would earn Bitcoin as a consequence. We're now very much more focused towards Bitcoin savings. So we're really interested in people who hold Bitcoin, but people who hold Bitcoin and actually aren't earning any value out of it. So one of the things that our current financial system facilitates quite well is the ability to put money with an authority who will generate interest for you. And granted, in the UK, the interest rates are pretty low, but you know, it's certainly better than sticking your cash under your mattress, for example. It's certainly a lot more secure. So at Magna.com, we operate a savings account where you can put Bitcoin into the savings account and you earn Bitcoin as a consequence. Just like retail banking, we have currently a fixed rate return. It's our monthly. It's accumulating interest per month. So kind of trying to unlock some value for those people who really look to put some value into Bitcoin, but kind of now don't know what to do with it, or they're just holding on to it. So just trying to kind of unlock some value for them. Okay, so we've got one more from Bob Stafaldi. He asks, I've read the benefits of using blockchain to track ownership of unique goods, land registry, paintings, solar auction, diamonds. Could this be used for shares, bonds, OTCs, equities, etc.? That's a good question. So one of the issues really crops up with using these kind of technologies comes down to actually issuing the asset in a digital format. So where the land registry is concerned, they are people issuing essentially the ownership of the land to another party. So if we were to talk about kind of a distributed ledger for land registry or a blockchain for land registry, would have to have, part of the protocol would have to say that the original transaction of giving somebody some land would have to originate from, for example, a public address that's owned by the land registry. So it would differ from Bitcoin in that sense that you wouldn't generate Bitcoins by mining, you would generate land registry ownership by a transaction which was issued by the land registry authority. So it really comes down to issuance and how you deal with issuance onto a blockchain-like system. And the same we said for like shares and bonds. You really need to have some form of authority issuing those shares onto a blockchain-like ledger. There is the possibility these companies issue their own shares, and assuming they publish their own public address, could verify that the initial issuance of those particular shares occurred from the public address associated with the company. So for example, if Google had public address 123, they could issue shares onto a blockchain for Google, and they could then send them to other people who purchase them maybe for cash, and they would then write a transaction saying, you know, the address 456 now owns this share to a value of something, you know, to a particular share account. And anybody can verify the trace of that share back to Google to verify that it's a valid Google share. So yeah, I mean, certainly ways of doing this. I don't know of anybody who really tackling that as a generic problem. Factom are doing it for NHS, and you've got the Everledger guys doing it for Diamonds. So people are kind of like applying that kind of technology, but really it comes down to how you deal with the issuance. Oh, I've got another one from Marcelo. Okay, so the question is how to avoid losing your private key. So in the example I gave, you know, your private key is on your hard drive because it's computer-generated key, essentially. So there's a few options. The most traditional option is backup. You can back up your private key just like you would back up, a Word document. You just put it on a USB stick and you put it somewhere safe. That's probably the easiest way of doing it. There are a few solutions which give you other ways of doing it. So you can actually turn a computer-generated key into a mnemonic. And this is something that's used by quite a few of the wallet providers. So a mnemonic is basically a sentence of words that represents your private key. So, you could have horse, carrot, bungee jump would be your private key, but in a sentence format. And people print that out on paper and throw it in a safe. And so if their hard drive gets smashed up or their key gets lost, they recover that key from the safe and basically regenerate the digital format from it. So there are ways of keeping your private keys safe. Ultimately, of course, if somebody else gets hold of your private key, it empty out your effective balance from the ledger and send it on some other address. So very much like if you lost all the stuff from inside it. So think of it that way. If you can digitally save it, typically on another drive, or paper print it out and put it in a safe. But ultimately, there are a few other security options. I recommend kind of Google for those. There's quite a few. But there's things like multi-signature wallets as well, which kind of give you some of that. Advanced security and hierarchical deterministic wallets will give you some security over the way you generate addresses for receiving funds and things of that like. So there are certainly options out there. Okie dokie, I think we've reached the answer on all the questions that have been asked so far. So it's been great doing this presentation. I'm going to hand it back to Adele, and I'm sure she'll close it off for us. And it's been great to do this. Thanks.
Wonderful. Thank you very much, James. And thank you everyone for all your questions. If anybody's interested in hearing more, James will be doing another webinar on the 25th of May. Thank you.